So models of dialogue and conversation. So dialogue's a big thing nowadays. A lot of people are interested in it, I think, and there's a lot of interesting work in the area. Neural models are playing a very big role in this, I think. It's not like dialogue didn't exist before neural models, but they make it very easy to build your own chatbot, so a lot of people are interested. So first, talking about the types of dialogue, there's kind of two types of dialogue. One is human-human dialogue, not like the kind we're having now. This is more like a monologue, but human-human dialogue between people, and then human-computer dialogue. And you can also say, why are they talking? So are they talking to achieve a specific task, or are they talking to just chat and waste time, basically? And I guess you could also say computer-computer dialogue as well, but we're not going to cover that in this time here. So I'm going to split this into two parts. Mainly, this is going to be about human-computer dialogue, and it's going to be about both chat and task-driven dialogue systems. First, I'm going to talk about purely chat-based systems. Does anyone use a purely chat-based dialogue system? Or
Define purely chat-based.
Purely chat-based, like it doesn't do anything useful.
What do you mean by use?
Well, like, your only objective is to spend time talking to the agent. It did in high school. Yeah, so there's certainly some people, some things that do this. Like there's a couple, Microsoft has a couple famous examples, like, I can't pronounce it well in Chinese. What's the Chinese name? Is it Zhao or something like that? Yeah. So there's a famous one in China that a lot of people use. There was also versions of this in Japan called Rinna, and then they released it in the US, and immediately people started trying to manipulate the system to make it say racist things, and then Microsoft had to shut down the bot. But you know, there are some bots like this in use, but I think they're not quite as wide use as things like Siri or Alexa that have some sort of task-based component as well. But these ones are easier to make because all you need is dialogue responses, utterances and responses. So I'll talk about these first. So there's kind of two paradigms here. When you want to do a dialogue, basically the idea of a dialogue is you have utterances and you have responses to those utterances, and this goes back and forth, A, B, A, B, A, B, between the speaker, who might be a human, and then the system. Generation-based models, basically they take an input from the user and they try to generate an output. That can be any arbitrary output as long as it's in the language that you're interested in. These are good if you want to be creative and come up with new things that have never been said before. There's also retrieval-based models, and retrieval-based models basically say nothing new is ever being said in dialogue. Everything is going to be rehashed from something that we've already seen. So what you do is you take the input and you find the most appropriate output. These are good if you want to be safe. In other words, you don't want to be generating ungrammatical or crazy outputs. You don't want to be generating racist outputs. So you do filtering beforehand to make sure you don't have anything in there that you really don't want your system to be saying. So you don't get news articles saying that your Google system or your Microsoft system is saying racist things to people. So both of these, I think, are used. Maybe the retrieval-based models are used more widely, and the generation-based models are researched more. So kind of the first, like, statistical data-driven generation-based model was by Ritter et al. In 2011, or as far as I know. Up until then, there's lots of work on template-based models or rule-based models, but this kind of brought dialogue into the statistical paradigm. And what they did was they basically took a machine translation system and they trained it on a parallel corpus of dialogue utterances and responses. And they had to do a lot of stuff like filtering the data to make sure the extracted translation rules were reliable. And the reason why is because unlike machine translation, there's a lot more variety in dialogue. So for example, if you have what time you get out, I get off at 5. This has a pretty good alignment between the words, right? So this is pretty clear. But if you have something like, if anyone's still awake, let's play a game named 3 Kevin Costner movies that don't suck. And then the answer is easier question, please. Then this is not very clear, right? It's pretty hard to decompose this into something that you can use as a translation rule. So this was a very good first start, but maybe this demonstrates how difficult dialogue is compared to something like machine translation, where you would have much more like close correspondences between the words. So the next kind of natural step is to apply a neural sequence-to-sequence model to try to generate dialogue responses. This was a really good idea, and it was such a good idea that 3 people had it at the same time. Actually, we also had it at the same time, but they were faster at implementing it than us. So, you know, at least 3 people had it at the same time. So, like other translation tasks, dialogue response generation can be done with encoder-decoders with attention. The simplest model, I think, is the Sheng et al. Model, where basically they just translate from the previous utterance. They take their neural machine translation system and train it on utterance response pairs. And then they can get something like this. High fever attacks me every New Year's Day. They did it in Chinese, so the translations are a little bit. And then get well soon and stay healthy. And we should go out with some cute guys to enjoy a great outing in such weather. It is indeed a very nice weather. So you can see that it kind of gets stuff with the appropriate topic here. Probably in this one, you don't want to be commenting on the weather. You want to be commenting on the cute guys. But, you know, hey, interests differ, I guess. So, okay, but this is the extremely straightforward way of applying your machine translation model to dialogue. But the thing is, dialogue and machine translation are very different problems. So there are a number of methods that people have been proposing to make the models more appropriate for dialogue. Oh, by the way, can I see a show of hands? Who's working on dialogue-related stuff or has worked on it at some point? Okay. So everybody feel free to chime in, because I think you know a bit about this as well. So if you have any interesting things that I'm missing, I'd love to have comments from the group. So one problem is that dialogue is much, much more dependent on global coherence and context. So considering only a single previous utterance will lead to locally coherent but globally coherent, incoherent output. So for example, because of your game, yeah, I'm on my way now. So if you just look at yeah, I'm on my way now, it's kind of underspecified about what you would be saying next. But if you know that the person's doing a game, then good luck seems to make a lot more sense, right? So you kind of need to pass this contextual information over multiple time steps. And this Sordoni et al. Model, they did it in a simple way of just encoding the 2 previous utterances, more or less, and then combining them together appropriately. An even more straightforward way, so yeah, sorry, this contrasts to machine translation, where context is useful, but it's not anywhere near as essential as dialogue. Another solution is to just use a standard architecture, but add more context into the architecture. So the Sordoni et al. One considers one previous additional utterance concatenated together. Vinyals et al., they go all the way and just concatenate together all the previous utterances and hope an RNN will learn. So an RNN, you know, can consider infinite context. So they just concatenate together all the previous utterances and use them to generate the next utterance. So based on this, they collected lots and lots of training data, and specifically from customer support dialogues. In customer support dialogues, basically you need to go through the customer. You need to go through an entire dialogue where the customer is describing their problem, and you're trying to find the most appropriate page to solve their problem. And they showed you can get something like, "Hi, hello. Could you please let me know what are the operating systems you're using? I'm using Linux, etc." And this seems to be relatively appropriate. Now, this being said, this is in a very limited domain of customer support, and they don't have many more examples than this, but you can see that you can get pretty impressive results with just this simple architecture if you have lots of training data. That being said, of course, when you move beyond limited domains and you want to get things to work without huge amounts of training data in your very limited domain, you need to be a little bit more creative. So one thing that people have used before is a hierarchical encoder-decoder model, which also has an utterance level recurrent neural network that tracks the dialogue state. So basically, you encode the utterance, then you output your prediction, basically. Then you input the utterance that you just output and encode this into the kind of utterance level RNN state. And this is simple. It's a simple two-level hierarchical model. That shouldn't be too hard to implement. But they show this does a bit better. And you can just train this on a large corpus of dialogues. There's also a number of other improvements that people have done. This is one work that's been done here at CMU, and this is a discourse-level variational autoencoder model. So one of the things I mentioned about variational autoencoders is that essentially, excuse me, they're a way to discover latent variables of some large segment of data that kind of compress the features of that large segment of data into a small feature vector. And that's the exact idea here. So they want to encode the entire previous dialogue context as a latent variable in the variational autoencoder, and they also use meta information such as dialogue X. So the idea is, let's see here. You have the utterance up here. You have meta information like dialogue X down here. You have another RNN that encodes these. And then you have a VAE style thing that gets a latent vector. Then that latent vector you use to generate your next utterance or regenerate the utterance that you just saw. They also have a thing where you predict the bag of words of the words in the utterance. And this is to help the problem that I mentioned in the VAE class about the VAE learning to ignore the latent variables. So basically, this bag of words helps prevent the VAE from learning the latent variables. It helps prevent that problem from occurring. So this is a pretty nice model. It's a bit more complicated than the Serban model, but it has the nice intuition that you want to capture kind of the higher level features of the dialogue context in a single vector. So these are methods for handling context that people have used. Are there any others that people feel I should be mentioning? Yeah. So I think that's a good idea. Is there a paper on that, or?
There is.
What's the? Do you have a name?
I find it on time.
Okay. Yeah. So I guess there's also memory networks. So actually, have we covered memory networks here yet? Okay. So yeah, that's a good thing to cover. I actually don't know if I think I'm covering them in the machine reading or reasoning part of the class. But basically, the idea of a memory network is you have a big block of memory, and this block of memory is basically a matrix or something like that. And then you have attention, something that looks like attention over this block to read from this, which allows you to turn this into a vector. So maybe 0.9. You're focusing on this particular section of the memory more than other parts of the memory. And then you also have the ability to write to this memory. So when you're in the write phase for the memory, you basically select which part of the memory you want to write to, and then you can write to that row. So the idea is you have this kind of like large memory that you can selectively choose to read and write to, which kind of makes sense for dialogue, because dialogue you have this long context and you might want to remember things and then look them up later. And Vasu will send the paper link to Piazza or something like that. Anything? I'll talk about this more in the knowledge knowledge and reasoning section of the class. Anything else? Okay. So the next problem, in a way, this is maybe even a bigger problem than the context problem. And the reason why is because this touches every single aspect of dialogue. It touches your training, it touches your evaluation, etc. And the problem is that dialogue allows for much more varied responses than other tasks. So for translation, something like translation, if you're going from English to French, there's a lot of different ways to say an English word, an English sentence in French. But even though there's a lot, they're still pretty limited. You know, you don't have. If you ask several translators to translate something, you'll probably get about the same words in all of the outputs. But for dialogue, this is definitely not the case. The content will also be different. So, for example, what are you doing? You can think of a million different good ways to answer this. So for me, obviously, the only correct answer is I am talking in front of a lot of people. I'm giving a lecture. I'm giving a lecture about neural networks or something like that. But this, is highly dependent on the situation, and there's, just a ton of different ways you can do this. Apparently, the most common answer for any question is I don't know. So I don't know. What are you doing? I don't know. That's actually not a really great answer, but if you compare it to what is your name, my name is Robert. My name is John. My name's John. I don't know. Apparently, is more common than all of the other names that we have. So, which one was that?
Just the, oh my god.
Oh my god. Oh my god. Okay. Yeah. What are you doing? Oh my god. I feel like that probability is a little bit too high there for that one. So anyway, there's a ton of different ways you can say things. So how do you judge whether this is correct or not? All of these are correct in a particular situation. So the problem is, if you train a regular sequence model, I think you can try this. There are dialogue corpora if you're building a sequence model. Just try to create a dialogue model and generate responses to random utterances. And you'll see most of the time you'll get something like yes or no or I don't know or thank you or something like that's supremely uninteresting. And the idea here is basically that we would like to avoid this, and we would also be able to evaluate our systems in the face of this. So this method is a way to avoid these kind of monotonous, uninteresting responses. It's a diversity promoting objective for conversational models. And the basic idea is really simple. You just train your model as you would normally. But what you want is responses that are likely given the context, but not likely otherwise. So what this looks like is you take the probability of your target utterance, t given s, and you subtract the log probability of just the target utterance multiplied by a lambda, which is a function about a constant indicating how much you want to promote diversity. And I think this is a nice method. It's really simple. There are probably lots of better methods that you could use to do this, but it's easy enough to implement. So if you're ever getting a sequence-to-sequence model that's giving you really boring, monotonous responses that are the same for every input, then this might be one way to fix it. So the idea is then, I don't know, might get a high conditional probability, but it also gets a really high unconditioned probability. So you subtract that unconditioned probability and penalize those common ones.
Excuse me.
Yeah.
Why do you think that's a good idea to subtract the probability of utterance? Wouldn't that sort of promote ungrammatical responses?
Yes, it would promote ungrammatical responses, and I think that's why they have the lambda there. So the lambda there, basically the lambda there is making sure that you don't discount them too much. That being said, I think if you manipulate the equations here, what they're doing is they're doing P of t given s, and then you're subtracting it by P of t, right? So if you yeah, is that equal to the maximum mutual information or something? Yeah. So so that kind of makes sense. You want things that are likely given the original one, but unlikely otherwise. So it's I understand the concern here, and that's part of the reason why I said there are probably better ways to do this. But yeah.
I feel like you could have some way of calculating the entropy of your given as entropy, minimize it so you have a entropy distribution.
Yeah, calibrating the entropy. So another thing that I would like to note here is that they're still taking the max. They're still taking the output with the maximum probability, which seems like maybe you should be sampling something instead. Another thing is my name is John, my name is Tom, my name is Jane, my name is Betsy, my name is Emily. You have all these different names, right? And the reason why you can't decide between them is because you don't know any information about the person who's speaking. So another reason why this happens is probably just because you don't have enough information to determine the utterance appropriately. So maybe better modeling is the solution as well. But yeah.
For ungrammatical model, wouldn't the value of log p given as be very low? Because
Yeah.
there are also models with the language as well.
Yes, it would. So I think basically what you're counting on is that there will be things where log of pt given s is high because it's grammatical, and then compared to that, the ungrammatical ones will be lower for both of them. But yeah, it's, as I said, this is a heuristic method that makes no guarantees about that. So what you really want is, a better objective function or something else where you're not just maximizing the likelihood. But as I said, dialogue is hard, and this is one of the reasons why it's really, really hard, I think. So as a result of using this method, you take their normal sequence model, and basically this one doesn't know about anything. So everything is I don't think, I don't know, come on, you know that, I mean, I don't know. And then the other ones, on the right, I did not get the report from a MI6 agent. You did the right thing, did you? You haven't been given an assignment in this case. I have been looking all over for you. You haven't, I'm losing my grip. I'm the only one in the world. Progress, maybe? Yeah. Yeah.
So how do you define dialogue? I mean, is it two people speaking to each other, or is it one continuous monologue? Because, for example, I'm losing my grip, I'm being given in the word, it's like one internal monologue just going.
No, dialogue is two people speaking to each other,
So then,
or multiple people.
if you say I'm losing my grip, and then you're saying that I'm the only one in the world, that doesn't make sense.
Yeah. So that's why I was being a little bit hesitant to say this is actually better on the right side. But you know, it's more diverse at least. So, but as I said, this is also a paper from 2016. There's been a little bit of progress made since then in neural dialogue models, but not a huge amount. So, but anyway, this is what it is. So another really major problem is diversity is also a problem for evaluation. So one thing that we could do, if you remember, we talked earlier in the class about tuning your models to optimize an evaluation measure. So let's say we had a really good evaluation measure that considers diversity or something like that. You could then go in and tune your models to basically increase the diversity or match the output in the face of diversity. So for translation, this can work. We know we have BLUE score. BLUE score is not perfect, but it's a pretty good measure of translation quality. And so we have methods that tune sequence-to-sequence models to optimize our BLUE score, and they increase translation quality. They help fix things like repeating words over and over again or getting things that are completely the wrong length. But the problem is, for dialogue, BLUE score is really not a good measure. And BLUE shows very little or no correlation with how well humans evaluate things. So this is an example here. We have a human score here. So this is a human score based on how good humans thought dialogue responses were. This is a BLUE score, and you can see that there's basically no correlation between these two. There's also a thing based on the word embedding average. This is just averaging the word embeddings and seeing how close they are to each other, and you can see there's no correlation. On the other hand, they asked two groups of humans to judge how good the dialogue responses were, and you can see there is actually good correlation between humans. So obviously there's something that humans know about dialogue responses that we aren't able to measure with the original measures. So there's been a few pieces of work to handle this. This work is done, to give a little bit of context, this is done by Microsoft. So the idea is that they retrieve good-looking responses. So they have some retrieval model that retrieves a whole bunch of responses for a particular utterance. And then they had a human evaluators basically grade all of these utterances, all of these output utterances for this particular input. And for example, I was about to text you, and my two cousins got excited because they thought you were Rihanna. I can't imagine their disappointment. They were very disappointed. That gets a relatively good score. Yes, luckily the whole thing feels very much of the past now. That gets a good score too, etc. And then you have the weather in Russia is very cool, which gets a bad score. So the idea is that now you have this multi-reference data set, And this multi-reference data set can be used to evaluate if you get closer to the good responses, then you're doing better. If you get closer to the bad responses, then you do worse. So the reason why I gave a little bit of context is this was done by Microsoft. Microsoft has lots of money. We do not have lots of money, unfortunately. So making this data set, as you imagine, you need to get a whole bunch of responses for a single, for a single corpus. You need to have human evaluators, multiple human evaluators evaluate each response. This is a very intensive thing to be doing. So because of this, we really wish we had evaluation measures that were less heavyweight. So that brings us to the next thing, which is learning to evaluate. So the idea is basically we take the context, we take a true response, and we take the actual response from the system, and then we use a regressor to learn to predict goodness. So basically, we learn to predict the human evaluation score. So this is very similar to our dialogue model. So basically, the dialogue model has context, and it has the true response, and you train the true response based on this, and then based on the context, you try to generate the model response. What this is doing is instead, this is during training time, it's taking the context, the true response, and the model response, and then at test time, you get the context and the model response, and you try to predict. No, at training time, it has the context, the true response, and the model response, and you try to predict the score, or try to train to predict the score. And then at test time, you get the context, the true response, and the model response, and predict the score. So basically what they showed here is that if you create a regressor that looks like this, it's able to predict the scores better than blue. It's able to get something that has much better correlation than blue. In a similar vein, there's also a method called adversarial evaluation. And basically the adversarial evaluation doesn't need these human annotated scores. The idea is that you take a context and a response, and you try to predict whether this is a true response or a machine response. And the more you can fool the adversary, the better job you're doing at dialogue. So these are two ways to learn to evaluate. So I should give one caveat about these methods from what we know from machine translation from a long time ago when we've had these methods to try to predict evaluation scores. And basically, learnable metrics tend to overfit a lot. They tend to look very good on a particular data set or a particular task, and then when you apply them to a new task, they don't work very well. This is a big neural network that has lots of parameters, so of course it has a lot of capacity to overfit. So I think the jury is still out about whether this is a good evaluation metric. I don't know if anybody here has used something like this before. Yeah.
So for the model, the Lowe model, they actually have a data set that they manually annotated.
Yes. Yeah, it's actually, I believe, the same data set is the one that I showed here. So they.
This was a follow-up to this one.
Yeah, I think so. Yeah.
So this data set was kind of like, these are two publicly available data sets that Ritter can one-to-one, but for the Lowe data set, they need their own data set.
Okay.
They have to, but it required like a lot of EMD workers to do that. Like, it was very expensive.
Right. But I guess the idea is if you can then train an evaluation metric that works other places, then that's great. But experience shows that that's not necessarily the case. So it's probably going to be better than blue, I guess, because blue, just isn't very good for dialogue. But the question is how much better? Will the correlation be, 0.8 or will it be 0.1 if you apply two reasons? So any other questions about this? Yeah. Or comments? Yeah.
Assume you have like a very large corpus of it, and say you formulate this as a problem of not. So you don't have like gold scores about different I guess maybe like Twitter or Reddit. Can you train something using negative sampling that trained over large corpus of data may generalize better over multiple data?
When you say negative sampling, you mean you would sample from responses that weren't?
Yeah, so for example, if you have a Twitter thread that becomes the context, the multiple responses to the Twitter thread are like valid responses to that context, and randomly sample from the data set are invalid responses. So you could potentially have like a huge data set that you can train more from. That may not work.
So I guess maybe that's kind of like the adversarial evaluation thing here. So you would try to predict, which one was a response to this particular dialogue context and which one was not a response. I guess.
You're training a model to predict the scores in this case, whereas in the adversarial thing, you're learning the Kannan frame.
Okay.
I think these negatives are really easy. You sample negatives from this top Twitter.
Well, so but you're trying to predict scores. So what?
So basically doing what the white paper did, but with like a huge data set, and because you don't have access to like a lot of annotators, you use this sort of formulation to build that data set.
Yeah, maybe. I'm not entirely sure I follow, but maybe we can talk about it later. Yeah. About negative sampling, I'm definitely going to talk about that in the dialogue response retrieval section, because it's very common to use negative sampling there. Okay, so another thing that is something that we should consider is that dialogue agents should have personality. So the idea is basically, a dialogue agent is not just a random response to anybody that anybody on the internet gives. It's from a very specific context. So the example of Twitter is very good from last time because, of course, I'm going to respond to something differently than the president would, for example. So, to use my running example. So. Of course, if we train on all of our data, our agent will be a mishmash of personalities. So where do you live now? I live in Los Angeles. In which city do you live now? I live in Madrid. In which country do you live now? England to you. So it's you get a different answer every time you ask a different question. So of course, we would like our agents to be consistent. There's been a lot of work on this from pre-neural times. I specifically cite this one because this one's really good, I guess. This paper basically, they train a generation system with controllable knobs based on personality traits, for example, extroversion. So they take the big 5 personality traits, which are things like extroversion and positivity and other things like that. And then they have a system where you can go from, that gives restaurant recommendations, either in a very extroverted way that says, basically, actually, I'm sure you would like Le Marais. It features friendly service and acceptable atmosphere, and it's French, kosher, and steakhouse place. Even if its price is $44, it just has really good food, nice food. And then the introverted person says, it seems to me that Le Marais is not as bad as the others. So you can see that extroversion is also, it's associated with verbosity, it's associated with a lot of other things. So they have these latent personality traits that they predict, and then they use this in their generation model. So I think this is really deep work, perhaps deeper than any of the neural methods have gone so far. But there are definitely neural methods that are taking this into account as well. So one kind of simple one is a persona-based dialogue model. Basically, it models each speaker in embedding space. So you assume you have a big speaker annotated data set like Twitter. And the big speaker annotated data set, because you have the big speaker annotated data set, you have 70,000 speaker embeddings, and then you just concatenate the speaker embedding with every word when you do generation. They also have a model of who the speaker is speaking to. So if they know who the speaker is addressing, you can also add an embedding for the addressee. So that idea there would be, if you know the speaker is somebody who's kind of high up in a particular company and the addressee is somebody who's low down in a particular company, you're going to speak in a different way if you're speaking down to your subordinate versus up to your superior, for example. So I think this is a really nice model if you can get lots of speaker annotated data. It could probably capture a lot of the things that they had in this more manually engineered model in latent space. One thing that I haven't mentioned, I actually forgot to add a slide on this, but it's pretty interesting work, is there's stuff like personal knowledge graph construction. So the idea is we're going to talk about knowledge graphs in a few classes. And basically the idea is you do information extraction to create a knowledge graph over the person that you're that you're speaking to. So if they say my name is Graham, then it extracts name Graham as one entry to your knowledge graph, and then uses that in Dialog. I believe this was Microsoft work shortly before all the neural dialogue stuff started coming out, but I think they've neuralized it at some point, but I actually forgot to search for the citation before coming here. So this would also be worth taking a look at. So there's lots of work on this. Also, Facebook just released a data set on this a couple days ago or something like this. So if you're interested in personalized dialogue stuff, Jason Weston will certainly talk about it in 1 week when he comes here to give the colloquium talks. So, are there any questions about these things? So this is the end of the generation section. Any other important things that I missed? I feel like there's probably a lot. But... No? Okay. So now I will move on to the retrieval-based models. So the retrieval-based models are models that basically get a dialogue response from a large database of dialogue responses. So this is one of my favorite new NLP technologies because I use it all the time. The idea is many things can be answered with templates. So you simply find the most relevant response out of the existing one in the corpus. And the reason why I use this all the time is because I answer half my email on my phone by using this new feature to Gmail, where basically if you pop it up on your phone, it pops up 3 dialogue responses under here. So if you get a response from me, it probably came from some random template on Gmail. Retrieval-based chat has been around for a while, maybe almost 10 years now. So the basic idea is given an utterance, you find the most similar utterance in the database and return it. The first work on this was in Korean, I think. So basically what they did was they had kind of a TF-IDF-based vector space model where they have their utterance response database. They have the user utterance, and they look up the utterance, the closest utterance in the database, and then they return the response to that utterance. So there's actually kind of 2 ways you can do this. You can either take the utterance and look up the utterance in the database and generate the response. Or you can also directly look up the response. In both of these I've seen, actually directly looking up the response can be better in a lot of cases because actually if you look at Twitter, for example, utterances and responses are actually seem completely random, like 30% of the time if you look at them out of context. So directly looking up the response can be better in many cases. So the similarity here was based on exact word match plus extracted features regarding discourse. And they also abstracted away named entities. So named entities obviously vary a lot. So you, to kind of abstract away from this, they made named entities like location, address, location type. So neural response retrieval, I think actually we were the first people to do this, like in 2014. I think this might actually have been the first paper using neural networks in dialogue, but nobody has corrected me yet. So if somebody knows, please tell me. And the idea is basically, up until then, response retrieval models were based on hard, like lookup of words. So just use neural models to soften the connection between them. So we used a thing at the time, which was kind of state of the art for paraphrase identification. And the idea is basically this utterance and this utterance are probably going to be a paraphrase of each other. So you want to find the one that's most likely to be a paraphrase and look things up. So we have Captain, we cannot keep going fast on these icy roads. We cannot keep going fast on these icy roads. Hold your fire, he's got a girl. Looks like he's got a hostage. I was actually very happy about this middle one. This is extremely cherry-picked. And then the third one, yeah, I can see that too, and I don't think it's so terrible. That's why I do all the thinking. So you can see that kind of this corresponds to your paraphrasing thing. The problem is it was kind of hard to take the paraphrasing model that was trained on a paraphrase database and apply it to dialogue, but this worked somewhat better than the previous methods. Yeah, and this uses the recursive autoencoder plus dynamic pooling. So the email retrieval thing, actually Google published a paper about this, and so they have a lot of details in this paper. It's actually very interesting to see what they had to do to make this actually work in your email inbox. And basically it's a model. The actual model they use is a generation-based model. So it's a sequence-to-sequence model where you take in your input and you generate the output. But it has several improvements to make it kind of stand up to actual use. The first thing is they do beam search, but they do it over the response space. So when you create a retrieval-based model, there's kind of two ways you can do this. One way you can do this is you can take your entire response space and just score all of the utterances in your response space. That, of course, would take forever because if you have 1 million potential responses to your emails, then you would have to score 1 million things every time somebody checks an email on their smartphone, and that would be a lot of GPUs or TPUs or whatever you need. So what they do instead is they basically create a trie. So if you think back to your data structures course on a trie, it's like the, and then after the you have dog, when, the man, etc. And they do beam search over this trie, but they anytime you have something that's not included in your space of acceptable results, you just remove it from your search space. So it's like normal search for a sequence-to-sequence model where you prune away anything that it doesn't exist in your database. They also have canonicalization of syntactic variants in clustering of similar responses. So one problem is if you look on your phone and try to do an email, and your response is basically all your responses are like thank you, thanks a lot. That's not going to be really useful. So they cluster together all of these similar responses that are in similar places in the space and try to get things from different clusters to make sure you get variety. They also do human curation of the responses. So this is to prevent Google from swearing at you. And this was actually very interesting this was very interesting. It's very useful for me, and looking at your responses, you'll notice this if you look at it closely. They omit redundant responses, so responses that are in very similar clusters, they remove. They also enforce positive and negative responses. So if you get a question, can you do a meeting today? And it's like, yes, I can do a meeting. Yes, I'd be happy to. Yes, that would be great. Then obviously, if you want to say no, then that's a problem. So they enforce that you have, they have a yes/no classifier, and basically enforce that you have at least one positive and one negative in your responses. Okay. So these are kind of the, this is the end of the chat-based dialogue part that I'm going to talk about. So next, go ahead. Yeah.
So in the previous slide,
Uh-huh.
when they actually do the clustering, do they do that on the embedding from the CPC, or how do they actually represent, how do they measure similarity basically?
You know, that's a good question. I read this paper a year ago, so I'm trying to remember the details. I think the answer is yes, but there's a very good chance that I'm wrong. So I think it was on the embedding space, though, if I remember correctly. Does anyone else remember this paper better than me? No.
They also use a label propagation type thing sometimes. Use expander algorithm as part of this pipeline.
I think that was part of the emission of redundant responses part, maybe. But yeah, they do a thing that tries to prevent things from being too similar. Yeah.
I haven't used Google's smart replies.
Yeah.
And anyone share their experience of using this feature?
Yeah, I was just trying to pull up an email that would have a smart reply. Let's see. So, so I have a good negative example actually. So I got invited to a meeting, and the answers are works for me too, good for me. So actually they failed at their enforcing positive and negative example there. But yeah, it's pretty good for English. I know it works for Japanese as of recently. So yeah, try it on your cell phone. Yeah, any other questions? Okay. So now I'll move on to task-driven dialogue. So task-driven dialogue is, as I said, probably more important. More people use task-driven dialogue systems by far than chat-based systems. Like your search functionality on your phone, be it Siri, be it Google Search, be it Cortana, is a task-driven dialogue system. It may have some chat functionality, but it's mainly to try to get you to places where you want to be. So chat is to get the user entertained, and what if we want to do an actual task? Examples of this are like booking a flight, accessing information from a database, using your phone, etc. So the traditional task completion dialogue framework, this was in the reading, if anybody did the reading. The reading was recommended this time, so it wasn't on the quiz. But in kind of semantic frame-based dialogue, you have a number of components. One is natural language understanding. And basically, you have a semantic frame that tells you what information has been spoken so far in the dialogue. And you try to fill the slots in this frame based on the user utterance. So very often, you'll hear people at a speech conference say natural language understanding. And when they say natural language understanding or spoken language understanding, they're actually talking about slot filling. They're talking about taking an utterance and filling in the slots of some sort of semantic frame. There's also dialogue state tracking, which keeps track of the overall dialogue state over multiple turns. This is like what information has been said so far. And there's dialogue control, which basically decides the next action to do based on the state. Then finally, there's natural language generation, which takes in the output of dialogue control and generates your natural language outputs. So it was very common, and still I think is very common in many practical systems to build systems this way, the division of labor between 4 parts. And there's, of course, neural models for all of these. NLU for slot filling, basically it's expressed as a beginning in and out tagging scheme. So you have show flights from Boston to New York today. So then you have slots or concepts. Where is your departure? Where's your arrival? What is your date? And also what are named entities and what are the intent and what is the domain? So what do all of these particular things mean? The domain here is basically kind of what app do I want to solve this? What app do I want to solve this problem? So if you think about this, if you're on your Microsoft phone, your Microsoft phone, you'll want Bing Travel to handle this query, right? Bing Travel has a thing where you put in a departure, an arrival, and a date, and say query, find a flight. So it's which API do which app do I dispatch this to? Intent is which API do I use, and then the slots are which functions do I fill into this API. They used a RNN CRF model for tags, so this is just, it's straightforward. It's not, there's not a lot to say here, but it works. The more interesting, sorry, go ahead.
Is BIO really the best way to go about this, because it's task-based? So BIO will give you a good, like you'll get partial accuracy even if you get just the, for New York, if you get U right, it'll still contribute to your final score. But actually it's useless because you need to get the whole chunk correct, otherwise you basically fail the task.
Yeah, and I think there's certainly better ways to do things. So you might want to do something like a semi-Markov conditional random field, which is something that you can use, but it's a little bit harder to program, so most people just use BIO schemes. But yeah. Okay. So we'll move on to the next one. So dialogue state tracking, what this looks like is you want to track the beliefs about our current frame filling state. So there's actually a dialogue state tracking challenge that gets progressively harder and harder every year if you're interested in this. But basically, oh, this is really small. So hello, which bus route? And the user says 61C, and then you get 61B, 61D, 61C is hypotheses with particular probabilities. You'll note that these are very familiar bus names if you're here in Pittsburgh. This is the Let's Go corpus created here at CMU, so that's why. And then, so your ASR system misheard, and you need to basically create dialogue systems that work in the face of this uncertainty in ASR, this uncertainty in natural language understanding, etc. So you have this kind of distribution over your beliefs. There's an RNN model that basically encodes multiple hypotheses and generalizes away by abstracting away from details of the outputs, etc. So this is a bit involved. I'm not going to spend a huge amount of time on this. There's at least tens of papers on doing this with neural nets, I think, now. So you can take a look at those as well. Then there's also language generation for dialogue from neural nets. I've already actually talked about this in previous times. This is basically a neural network model that takes in structured data and it conditions LSTM units based on the dialogue input, the output in English. And they have this DA cell. This is the dialogue act cell. And the dialogue act cell is supposed to encode long-term information. So they treat this differently based on the dialogue acts than they do the other inputs to the LSTM. But it's a minor change. But the more important kind of contribution of this was to show that this really does better than any of the previous natural language generation approaches, and this was one of the big reasons why people moved to neural nets for dialogue in text-based dialogue, I Now these were all kind of old things in the end-to-end framework where everything's split into its own individual module. And I think maybe the more exciting thing is recent work by Williams et al. On end-to-end dialogue control for task-based dialogue. So I think this is really cool work. It also looks super hard to implement. So I don't think it's something that would be easy to reproduce. But basically the idea is you train an LSTM that takes in text and entities and directly chooses an action to take, be it a textual reply or a API call. So this is really interesting because it's kind of like mixed chat-based task-driven dialogue. And so you have this big framework where you have like entity tracking. You also have an utterance embedding, and you have an API call history, and your action from the previous state. So, or API result history and action from the previous state, and all 6 of these different types of actions get input to your RNN. So you have a thing that's basically observing your entire dialogue context. And based on this dialogue context, you make a prediction, and your prediction is basically a dialogue response. So it's either something from your dialogue database, or it's an API call. So I think this is pretty nice. You think about talking to your phone. You either want a response that says something witty, like saying Siri, "Will you marry me?" And I forget what Siri replies to that. What was it? Thanks, but no thanks, or whatever. Or you say, "Siri, how old is the president of the United States?" And it replies to you the appropriate answer to that. So. And then based on that, you're embedding all of your stuff. You choose an action type, you choose an API, or based on the action type, you choose an API or text, and then you return the API result back into your RNN, etc. This is trained using a combination of supervised and reinforcement learning. So they start out with some supervised kind of gold standard dialogues, and then they let it loose on the users and train it with reinforcement learning. So. I looked at this work and I was like, wow, that's really cool. What else is there to do? So I feel like this was really very solid work that handled a lot of the problems in this kind of mixed initiative dialogue. So I'm sure people here, I don't know if anybody tried this in the Alexa thing. I guess the Alexa thing is just kind of chat driven, right? There's no task-driven components. So okay, yeah, that makes sense. So yeah, that's all I have for today on dialogue systems. Are there any questions or discussions or things I missed here? Yeah.
So more of a comment. But there has been some recent work wherein one of them is like after you're chatting with the dialogue agent and if the dialogue agent doesn't know the answer, it asks you. So like feedback oriented dialogue.
Okay. Yeah. So that's very interesting. I don't know that paper. So it's called feedback-oriented dialogue?
I don't remember. I can post it here.
Okay, cool. And
Other is quite frequently used in task-oriented dialogue systems. But what about chatbots? RL for chatbots.
RNNs?
Reinforcement learning.
Oh, reinforcement learning. Yeah, there is a paper on reinforcement learning for chatbots. I think there's the paper I'm talking about is by Jiwei Li. It's a paper on reinforcement learning for chatbots. I think it's less clear why you would want to do that, because if you have a lot of data for natural chat, then it becomes less necessary to use RL because you can just train with maximum likelihood. What you can do is you can assume that if people chat with you longer, or they chat with you with more positive sentiment, then you're probably doing a good job. So then you could use that as your reward function, for example. Yeah, I don't know. Does anyone know of like work that is on this? seems natural, but yeah.
The only way you can do adversarial training is by training it by reinforcement.
Well, training it by some method to differentiate through discrete variables. So it doesn't need to be reinforcement learning, and actually something like Gumbel softmax would probably do better there, but or professor forcing, for example. Like a pure reinforcement learning problem where you actually legitimately have delayed rewards and you have to do rollouts, that would be something where you're learning from the user response. Yeah. Yeah.
There's also this field of like talking about something.
Uh-huh.
Where you're given like an image and then you're chatting about the image or something.
Okay.
That's maybe an interesting area of research, but that's pretty new as such.
Okay. Cool. Yeah. So I imagine you like embed the thing that you're going to be talking about, and then.
Like the way they phrased it was it's a two-player game where two agents are talking to each other about an image, and they kind of end up matching the features that they learn from the.
Oh, I see. Okay. But is this between computers and computers or humans?
Between two agents.
Okay. Okay. So I talked about that a little bit in the latent variables part. I don't know if that's the same one that you're talking about. Oh, okay. Yeah, okay. So maybe that's it. Here I've exclusively talked about human-computer dialogue as opposed to. So if you're not aware of this, if you're interested in these kind of things, there's kind of a classic paradigm called the map task, where one person has a map, or two people have a map, but only one person has the X on the map, and then the person has to. The person who has X has to explain how to get to the place.
There's a paper on this at IKEA last year. Like,
Okay.
It's about how like language emerges when you have like two agents that want to communicate.
Yeah. Yeah. So I think that's the one that I was talking about in the latent variables class. So. There was also a paper at NLP that says this isn't really language, it's just kind of symbols. So there's, my impression is that agent-agent communication and human-agent communication are pretty different to almost the point where you, like an autoencoder is agent-agent communication, right? You have a vector of continuous variables, and you're communicating between your encoder and your decoder what the content is. So. Like agent communication in discrete sequences, I don't think it's like, why would you call it a language any more than you would call a vector a language? But so I think that's kind of the point of the NLP paper that was saying this agent-agent communication isn't actually discovering language; it's just discovering a sequence of symbols unless it demonstrates something that has features of language, like compositionality or things.
What if you like multitask train, this kind of, like let's say you have two agents that are trying to communicate with each other, and you also multitask, with some other tasks that can help like ground this like artificial.
That actually does work. So you had a distributor which kind of differentiated whether the dialogue you send across between two agents actually makes sense.
Okay.
It does work to make it more grounded.
Okay. Oh, that's really cool. So one paper that I can refer to this that I assume this isn't published yet.
There was another paper on Western board was from the ladies that said Jason paper was also that. And that would be applied because that concept can apply to it setting and it works better.
Okay, cool. Yeah. So again, if we can post these papers, I think that'd be great. There's the other one. By Jacob Andreas about translating neuralese. And this and basically what this is doing here is you have communication between two agents, and then you want to basically make the communication between the two agents elicit the same action of the agent where it elicits an action from a human. So it's kind of hard to explain, but the paper's explaining it much better than I do. But I think that's similar to your multitask idea. Yeah, these are all good references. As I said, there's a lot of people here working in dialogue more than I am, so I think this is great. Are there any other like major things that I missed? Okay, if not, I'll be happy to have everybody post the references on Piazza, and we can discuss more there. So, thank you.